Thanks for the introduction. Thanks for having me here. It's great to come back to Princeton. So I changed my talk title and topic a few days ago, just in case you checked it earlier. So this is about designing explicit regularizers for deep learning models. I guess it doesn't sound it is so kind of classic, right? So explicit regularizers. This is a very classic notion. It doesn't sound more enough for deep learning, I guess. So I guess what I'm going to do is to spend probably a few slides to justify why this is still somewhat relevant for a deep learning regime, and empirically relevant and theoretically relevant. And then I'm going to talk about what regularizers we design and what experiments we have seen that shows that the regularizers can improve the generalization performance. So we care about generalization, so I like to start with the outcome razor. So the philosophy is that the simplest solution is most likely the right one. I think despite that we found a lot of conventional wisdom in machine learning has been kind of challenged in deep learning area. So still the Occam's razor is something what we believe. I guess in Misha's talk yesterday, so he also mentioned some difference, slightly different kind of Occam's razor from the kind of conventional cases. So let's say suppose we still believe the Occam's razor, right? In a more technical term, so I guess I'm going to translate to low complexity solutions likely generalize well. So and the question is that what is the measure of the low complexity? Whether the measure is by the number of parameters in your hypothesis class, or the measure is by some norm of the hypothesis class, or the measure should be some smoothness and all other properties of the model. So I guess what are the correct definitions? Maybe there's no unique definition of the right complexity, but what are the correct definitions for deep learning? So this is the question. I think if we can answer it, we can hope to understand the generalization of deep learning, and then we can use the complex measure for regularization. So I guess one of the way to kind of understand what are the correct measure is to think about the regularization effect of the algorithm. We know that the algorithm provides a very strong regularization effect, and people refer this to implicit regularization or algorithmic regularization. So the general paradigm of this line of research, if I were, I could summarize, consists of these 2 points. So the first part is that you say the algorithm prefers some low complexity solution. Right, and then whatever the complex measure you figure out, the algorithm prefer, then that is the complex measure you want to use to show your generalization. And then the next step you say this low complex solution generalizes well. Right, for NTK, the low complex solution is the solution that is close to initialization, and for other cases, the low complexity is measured differently. Sometimes it's the nuclear norm, sometimes it's the L2 norm, so on and so forth. So if I have these 2 points, then we can understand existing algorithms, because this is characterizing how the existing algorithm is doing, and then we potentially can discover a complex measure, a new complex measure, because whatever the algorithm is regularizing, that's the complex measure we discover. So I guess to kind of just expand on this a little bit, we have found different kind of regularizations that the algorithm can have. For example, one of the regularization comes from the learning rate. So here is an experiment that shows that actually if you have fast training, you may have worse generalization. So in some sense, sometimes you want to have a large learning rate so that the training is not fast enough, and it kind of gets somewhat kind of stuck, but still the generalization is better, right? So here, I guess the exact figure probably doesn't really matter that much, but we can see that if you use large initial learning rates, then the generalization, the solid lines, the green solid line is better than the orange solid line at the end. So generalization of the large learning rate is better than the generalization of small learning rate. However, for training, we have the reverse phenomenon. So the training of the small learning rate algorithm is faster than the large learning rate algorithm. So I guess this is one example where people have found that algorithm can regularize. Actually, if you run different algorithm, you have different generalization performance. And this also says that the lack of understanding of the generalization hampers the study of the optimization. Actually, a few years back, with Elad and other collaborators, we tried to design better algorithms, better second-order algorithms, and we found that the algorithm could work very well for training, but they didn't work very well for generalization. So and here what are the models preferred by the large learning rate? We have some recent results that try to explain this, But basically, we can only explain it for some very toy cases with some pretty involved analysis, unfortunately. So I guess the point is that if you use noisy gradient descent, if you use gradient descent with large learning rate, then you're going to have a large noise in the gradient. And effectively, the noisy gradient restricts the complexity of a two-layer neural network to be a linear model. When you have noise, then actually your model complexity is not as big as you may think, right? Even you have a two-layer network when you train, actually it is effectively just a linear model. Of course, you need to work on have another set of ideas to kind of like see exactly this kind of like a delayed effect of generalization, because here the generalization at the beginning is worse and the generalization at the end is better, and the initial learning rate matters. So you have to do some other things to see why the initial learning rate also matters. But I guess the key point here is that the models learned by large learning rate are somewhat kind of simpler than the models learned by small learning rate. And I guess there are other kind of preference of algorithms. For example, we have understood like people have understood that initialization matters a lot, and if you have large initialization, then it prefers to stay close to initialization, and this is the NTK regime. And this result is very nice result by Chizat and Bach, shows that basically with a little bit over parameterization, then the only thing you care about is the initialization. So if you have a large enough initialization, then you can get into the NTK regime. And on the other hand, I guess probably you'll see more about this in Nati's talk in the afternoon. So if you have small initialization, then the algorithm prefers the rich regime. I guess Nati will define exactly what rich means. But generally, you'll see something different from the NTK regime. So in certain cases, you are going to have L1 or nuclear norm preference.
Actually, I'm not sure any of these apply because of batch norm. I mean, all the networks use batch norm, and this is completely scrambled.
I think empirically they do apply. We did have a paper on this that empirically shows that you have to use small initialization when you don't have batch norm. Yes. So when you have batch norm, then this may not be that relevant.
And all deep nets use that.
But in some sense, what the batch norm is doing is to make in some sense the initialization on the right scale and the learning rate on the right scale. Okay, so but I agree. So all of this, so batch norm is also another kind of regularization. So generally, I'm just using these examples to show that different pieces of the algorithm could regularize differently, and they have there is a rich enough phenomenon for us to study about the algorithm's preference. So initialization, batch norm, and these are all examples. So, but I guess, yes, the question I want to discuss, the main question I want to discuss in this talk is whether this is the only approach towards understanding generalization in deep learning. So are there any other approaches? So I'm not saying that this is a bad approach. This is a fantastic idea to understand algorithm regularization, but whether there are any other approach. As you can see from the title of the talk, what I'm going to propose is that there might be some other approach that also makes some sense, and this approach is somewhat kind of a classic one, which is we use explicit regularization, and I think this also deserves some attentions. So I'll kind of like to justify why this makes some sense. So I like to kind of reflect on the paradigm that we have to understand algorithm regularization a little bit. So just to go back this kind of like paradigm, if you think about it, about existing papers, then we realize that actually for most of the works, if not all of the works, the challenge is the first step. So we spend a lot of effort, at least technical effort, in the first step to prove that the algorithm converges to certain type of solutions. For NTK, you have to do the you have to control all the kind of like how fast you move. For like a small initialization, I think in some of the papers we have to control certain norms, so on and so forth. So this is often the most technical part of the proof. And the second part is often easy, actually. Why low complex solution can generalize. In the existing paper that we can analyze this full pipeline, the second part is often the easiest part among these two. So, and also all the analyzable deep learning algorithms if they are analyzable, then they can be somewhat replaced by a simpler or more explicit one. By explicit regularization or by some kind of kernel methods or some interactive, iterative kernel method. I'm not saying that this is a bad thing, because if you can do this for the real deep models, then actually it's great, because we can simplify existing algorithms by something that is principled and also works pretty well. But I guess my point is that the second part of this paradigm, the low complex solution generalized well, this part we are not spending that much of effort here to understand that part. On the other hand, so I'm going to talk about explicit regularization, and I think the difference here is that the plan or the program is that in the second part, right, so about the complexity solution, low complex solution generalized well, we are going to try to find complex measure that leads to a better generalization. So before, what we did is that we passively think about the complex measure preferred by the algorithm, right? So whatever the algorithm prefers, that's the complex measure you are going to use in your analysis. And here I'm proposing that maybe there are also other complex measures which are better, probably even better than what the algorithm prefers. And those can lead to better generalization. And suppose you have such a complex measure, then maybe, so then what you do is you say, I'm going to regularize the complexity when I train the model. And then I just hope the optimization can magically succeed, because this part, the computational part is often difficult. So in some sense, you just, this is kind of like cheating in this sense, because you are just crossing your finger to talk about the bottleneck. So you're not addressing the bottleneck. You are saying, for the bottleneck, I'm not going to deal with it because I don't know anyway. But then this allows us to focus more on the second part, where we think about what's the right complex measure that can lead to a better generalization. So as consequences, first of all, we are not going to understand existing algorithms. So this is a big limitation of this approach. You are not going to understand why the algorithm can regularize. But in return, we may design new complexity and regularizers. And we may design new algorithms because we just regularize in the training. And also, hopefully, at some point, we can have some separation of statistics and optimization, because if you have enough regularization, then you don't have to care about what the algorithm is regularizing. So all the algorithms on the right, with the right regularization term, will converge to a good solution. So, and I think there could be other benefits. For example, the double descent phenomenon that Misha talked about last time. If you tune the right, if you tune the regularization strength, then often you wouldn't see it. At least you wouldn't see it as strongly as the no regularization case. So maybe there's no double descent mystery. And also there are kind of other counterexamples, again, for example, for those of you who are familiar with the paper by Nagaranjan, this is very, very interesting paper that shows that uniform convergence cannot explain the generalization of deep learning, but those kind of instances are solutions that are obtained by a particular algorithm. However, if you regularize in those cases, then uniform convergence could still apply. So somewhat of a long shot is that perhaps with the right regularization term, then we can replace the implicit regularization at some point. Of course, just to be clear, I think on the left-hand side, this may also lead to new complex measures and algorithm, right? Because if you understand existing algorithm, the working of existing algorithm, and then you may, it may inspire you to design better a complex measure and algorithm. So I'm not saying that the left-hand side, the plan is better than the right. So the right-hand side is better than the left-hand side. Actually, it achieves weaker goals compared to the left-hand side. I guess my point is just that. There's another way to approach this problem, which also makes hopefully a little bit of sense to you. Okay, so suppose I kind of convinced you that the explicit regularization still deserves some study. Let's see how do we study them. So how do we kind of like find out what is the right complex measure? And the way that we find out the complex measure is that we try to prove generalization bounds and use the right-hand side of the generalization bounds as a complex measure. So at the end of the day, the bound we prove is of the following form, which is not exactly what people often do in the classical statistical learning. So let me just parse this. On the left-hand side, we have generalization error, which is the test error minus training error. And on the right-hand side, we have square root, some complexity measure over n. But here I want to stress that the complexity is a complexity of a single model and a complexity that depends on the training data. So for example, if you do this dimension, then this complexity will be a complexity of the entire hypothesis class, right? So I guess just to connect this to Misha's talk, Misha has argued that there's a fundamental limitation if the complexity only depends on the hypothesis class and the data distribution. But here, we are interested in this kind of like complexity measure where it depends on a particular hypothesis and also it depends on the training data points. And this would allow us to get better bounds and kind of like, at least in my mind, kind of circumvent some of these fundamental limitations of the old bound. So, and if you kind of like check the kind of like information dependency here, so basically on the right-hand side, on the left-hand side, this quantity depends on F, depends on training data, and depends on training distribution. And what this bound is really kind of like kind of hiding is basically the training distribution. On the right-hand side, we don't have dependency on the training distribution. In some sense, whether the bound is tight or not depends on how much you know, how much inductive bias, how much prior knowledge you know about the training distribution. And if you know the training distribution, you can get very, very good bound. So just to briefly summarize some of the related works in this line, so some of the early works tries to prove complexity bounds that are of the classical form, where the complexity measure is some kind of like a function of the norms, and often is actually a product of norms of the weights, and also a function of the output margin, which I'm going to define in a minute. And Sanjeev's team has a work, very nice work that use compression-based ideas to prove such generalization bound. So the complex measure is a function of F and the training data. Although I think in that particular paper, the generalization bound only applies to the original, the compressed model. But now there are many new works that try to extend this to the original model. In some sense, our work is really just one way to extend the generalization bound in this paper to the original model, the uncompressed version. And I guess there are also pack-based based data-dependent bounds by Dan and Carolina and Nagaranjan and Coulter. So these are bounds of similar type, but they are obtained from the pack-based framework. And we are going to use more kind of like a random marker complexity-based framework. Right, so I guess the point here is that, what is the right, so how do we prove this kind of complexity generalization bound, and what's the corresponding complex measure in the numerator? So I'm going to show you one of the very recent work where we have, in my opinion, quite simple bound, and based on this notion, we call Alllayer margin. So the bound is, looks like this. Let me parse it for you. So of course we have to talk about the randomness with high probability of the randomness of n data points. The generalization is proved to be smaller than this term, up to some second order term, which doesn't really matter. So so it's 1 over n times the square root, basically some kind of average of this so-called margin of xi. I'm of xi is the so-called Alllayer margin, which I'm going to define in the next slide. And here we just have some kind of average of the inverse margin. And then we have the norm of the weights. But we don't have the product of the weights. It's really a sum of the norm of the weights. So this bound is kind of simple in some sense. I guess if you think about oximeter in the scientific research, I would like to say that because it's simple, I feel like, at least in my mind, I feel like because it's simple, it's probably close to the right kind of techniques we should be looking for. So of course, a lot of kind of like things are swept under the rug of the Alllayer margin, which I'm going to discuss. So for linear models, this M of xi, the margin is just the standard output margin. and the theory actually was essentially proved in one of the earlier work by Nati and collaborators. So, okay, so what is this Alllayer margin? So I'm going to only use binary classification to define it. So recall that if I have a linear model, then what happens is that the margin of an example is basically the distance of this example to the decision boundary. We have a decision boundary, and the classifier is called W. And in mathematically, basically the margin is the label. It's a +1 -1 label times W transpose X, which is the output margin over the norm of the classifier. And the challenge to kind of extend this notion of margin to nonlinear deep model is that if you have to kind of like if you want to define the normalized output margin, you know that you want to say this is my model output before the softmax, right? So and I want to normalize it by something, right? So here I'm normalizing the L2 norm, and here the question is what I'm going to normalize. I'm going to use to normalize the output margin, right? Because if you scale everything, then your output margin will become bigger and bigger. So certainly some normalization has to be there to make sense of this. So and the question is, what normalization there should be. And people have used the product of norms and so on and so forth. And we basically kind of like propose different ways to kind of think about normalization. So the way that we thought about this is that we say, let's go back to the linear model and see whether for linear models there's an equivalent. So we have an equivalent way to define the margin. And here is the equivalent way for linear case. So basically what you say is that I'm going to perturb my data point by delta. And after perturbation, I'm going to cross the boundary. So basically, before I'm classified correctly, and now after perturbation, I want to be classified wrongly. And I'm asking what's the minimum perturbation I need to cross the boundary. And it turns out that if you just solve this minimization problem, it's equivalent to the margin that we have defined, up to some norm kind of scaling. So, and inspired by this, we can define analogous Alllayer margin for the deep models. So the definition is as follows. I'm kind of like sweep a lot of technical things under the rug, but the idea is that you say, I'm going to ask how the minimum perturbation I need to cross the boundary, basically. So I have a perturbation on every layer. So R is the depth of the neural network. So I'm going to perturb all the layers by some amount so that the output is flipped to be incorrect after the perturbation. So, and the minimum amount of perturbation I need on all of these layers is defined to be the margin of my neural network.
Perturbation is on activation.
Perturbation is on activations. These are vectors. Yeah, so we need to measure the norm of all of these vectors. Actually, we measure the norm, L2 norm of each of these vectors, and then we take some other LP norm. Yeah, the details don't matter that much. I guess you can change the norm.
Yeah, so that was my question. So it's a multi-Q norm which you can change?
Yes. So I think the norm actually, at least for the purpose of this discussion, it doesn't really matter. In certain cases, you have to kind of be a little bit careful to get the best bound. But at high level, most of the norms are fine. Yeah. So right. So this is the definition of Alllayer margin, and with this Alllayer. In other words, so what do I mean by this output is flipped? Basically, I mean that I'm going to apply all of these perturbations. Then my classification will be wrong. In the sense that my label times my output is going to be less than 0. Right.
Is the perturbation before or after activation?
It's after activation. Yeah, I think the precise definition doesn't matter that much, and you can define it slightly in different ways. Because if you perturb after activation, in some sense, you are perturbing the next layer up to a linear transformation.
So you mentioned this, but is it a simultaneous perturbation, or do you perturb like a layer at a time?
Yes, so it's a simultaneous perturbation. So you are allowed to perturb all the layers together, and that does has some small effect at the end.
When you say the perturbation, the exact norm doesn't matter. I mean, it will give you completely different complexity measures, right? Isn't that what exactly would determine the complexity measure? The choice of norm on delta?
Yes. So to have the formal theorem, yes, the precise definition of perturbation does matter. So we need to actually rescale it a little bit. So your perturbation has to be measured relevant to the norm of the activation. So basically you say I'm going to perturb delta times the norm of the activation. That's how we measure the perturbation. But but all of these are kind of technical. So if you change them a little bit, you can still have the correct theorem. It's just probably not the optimal one.
Do you have any idea about the complexity of doing this computationally?
Yeah. So I'll talk about that. We have a heuristic algorithm that can maximize the margin, and it slows down by a factor of 2, for example. So is that the question?
Yeah. Do you do exactly or is it approximate algorithm? Do you have results for that algorithm too?
I have some empirical results. Maybe let me.
Is it implementing this exactly or is it
Not, it's an approximation. It's a pretty rough approximation. Yeah. I'll talk about it. Yeah. And actually, there's a very simple proof. I'm going to only use one slide to talk about the proof idea. So recall that we want to prove that the generalization is less than some average of the inverse margin times the norm of weights. So the tool we use is the following idea from, again, the Nati's paper, so in 2010. So basically there's this, suppose there's some function m that correlates with the 0-1 loss, in a sense that if you are misclassified, then you have 0, and if you're correctly classified, it's positive. So actually this works for any function with this property that correlates with the 0-1 loss. Then you can say if you use standard tools, then you just use uniform convergence on this, m, the margin, and then there's a kind of like a machinery to say that it suffices to bound the complexity of m. So just basically because m correlates with the 0-1 loss. So if the complexity of m is small and it correlates with the 0-1 loss in the following sense, I think I omitted the one part, which is you need mx to be bigger than 0 if x is classified correctly. So then with these two properties, you can just show the generalization bound of the 0-1 loss. So this is the standard tool we are using. I'm not going to talk about details. And then with this tool, the only thing that is remained is to talk about the complexity of m. And here, somewhat by design, the complexity of m is actually very simple. So because m of x is a Lipschitz function in the parameters. So and to see this, I guess it's basically you just need to kind of like use the definition of the arc mean of the margin. So if you perturb your parameter, then perturbing the parameter is kind of equivalent to perturbing the activation. So that's why you are Lipschitz in the parameter. So basically, at a high level, this is the only thing you need to prove. You need to prove that m of x is Lipschitz. There's no any other thing, and then you use uniform convergence from Nati's beautiful paper, and then we get this result. So in some sense, all the kind of like the difficulty is kind of hidden in the definition of mx that makes sure that m of x is Lipschitz in a parameter. And that's why we have to talk about this kind of like a simultaneous perturbation, so on and so forth. Right. So in some sense, m of x reshapes the m of x reshapes the heterogeneous geometry into a homogeneous one. I guess I don't have much time, so I will just probably skip this. Oops. And also we can, because as you can see that the definition of the margin has some kind of adversarial part in it, right? So you need to talk about the worst case perturbation. So actually, as a byproduct, very interestingly, this leads to also a bound for the generalization of the adversarially robust loss. And the loss, the bound is pretty simple. Basically, the only thing you have to do is that instead of measuring the margin on the data point xi, you are measuring the margin in the neighborhood of this data point xi. So if you're in the neighborhood and the margin is good, then you have the robust classification generalization bound. So now let's quickly talk about how do we maximize the Alllayer margin and how do we use it in practice. So it's a max-min problem, right? Because we want to maximize the margin. The margin has a definition. The definition of margin involves the minimum of the perturbation. So it's a max-min problem. So we just use some standard, idea from robust optimization. You just alternatingly minimizing and maximizing the two parts. So empirical results show that actually this can improve on top of pretty strong baseline. So we have taken this well-tuned white rise night 16 or rise night 28, and the baseline for CFAR has 4%. And we have tried various settings where you have the standard setting, or you have some kind of like a no data computation where you lack some regularization, or where you have some random labels. Those are cases that probably you need more regularization. And you can see that across the board, we have improved the results in terms of generalization, and for both the data sets CFAR 10 and CFAR 100. So, and also we have tried this on the robust classification. It is known that for CFAR, the generalization of robust loss is one of the bottleneck, because if you use these standard models, then your generalization of the robust loss is something like 50%. That's the test robust error. But actually the training robust error is pretty close to 0. It's something like probably 10 or 20%. And we applied this kind of like a maximized margin technique, and we found that we can improve the robust accuracy or robust error as well. So I guess I'm running out of time. So we also have used this for other cases where you have imbalanced data set. So these are cases where you need stronger regularization, because you have kind of like this heterogeneous data set. Either you have noise or imbalanceness or some other kind of like non-standard type of data set, then regularization is more important. And we tried it on the imbalanced data set, and we also found pretty good improvements. So I guess the catch here is that if you want to regularize the imbalanced data set, then you have to regularize the complex measure of the minority classes more strongly, because those are the examples you want to kind of focus more on, and they have worse overfitting. So that means that the complex measure has to be a function of the training data point, so that you can regularize each of the training data points separately. Okay, just to wrap up. So the kind of like the workflow that we kind of like propose here is that we design explicit regularizers through this kind of generalization bound, complex measure, and regularization workflow. And we have seen that tighter bounds leads to better empirical results, at least so far. In all of these empirical results, we didn't really actually tune the hyperparameters much. Like we ran it once, and somehow it just magically, with one or twice, once or twice trials, then we got pretty good results. I guess some of the obvious open questions are, how do you have bounds for other data-dependent regularizations? I guess dropout, data augmentation, mix-up, cutout. These are all existing data-dependent regularizations. And how do we characterize the generalization performance of them? And can we design new generalization techniques, new regularization techniques from the inspiration of this? And of course, optimization is a big issue here, so we don't know how to regularize how to optimize the regularized loss. I think this is going to be a very challenging question to regularize some of this, to optimize some of these regularized loss. And a slightly broader kind of vision is that I start to realize that for heterogeneous data sets where you have noise or imbalance, then the regularization is more important empirically. And those are probably places where some of these explicit regularization technique can have a more empirical impact. Thank you.